Hello, welcome. This is Austin from Tclassified.com. Today I'm going to be making a presentation on the topic Deep Learning as a tool to predict flow pattern in two-phase flow. Project proposal by Augustine Emeka Ekene. The term flow pattern refers to the spatial distribution of the phase which occur during gas-liquid two-phase flow in pipes. When gases and liquid flow simultaneously in a pipe, the two phases can distribute themselves in a variety of flow configurations. The flow configurations differ from each other in the interface distribution, resulting in different flow characteristics. In essence, when there is a mixture of gas and liquid, when both of them are moving simultaneously in a pipe, you can see different pattern of flow because of the combination of this gas and the fluid. Now you can have things like bubbly flow, wavy flow, plug flow, slug flow, stratified or annular flow if you're considering a horizontal pipe. Now we are having this kind of flow because you are having a combination of gas and liquid flowing together inside a pipe. So we're going to be studying how this classification is done, considering the features which they depend on, which is the superficial velocity of the gas and that of the liquid, as well as the pipe diameter. So we want to do this classification. That's the essence of this learning. So flow pattern simply means, is it having the pattern of bubbly? This is how bubbly flow pattern looks like. This is wavy flow pattern. This is plug flow pattern. This is slug. So when the liquid and the gas are mixed, moving together, do you see bubbles and the fluid and the liquid, or do you see it in the wavy form like this? So what is the flow pattern? So this is what we call flow pattern: the arrangement, the spatial distribution of the liquid and the gas inside a pipe as they flow. So let me get back to this. Now, determination of flow patterns is a fundamental problem in two-phase flow. Whenever you hear two-phase flow, it simply means gas and liquid flow. Indeed, all the design variables, namely phase velocity, pressure drop, liquid hold up, heat and mass transfer coefficients, resident time distribution, and rate of chemical reaction, carry out a better design of two flow systems. So for you to determine all these variables that I've mentioned, you need to know the flow pattern. So in a way of diagram, what are the flow patterns that we have? If your pipe is horizontal, these are the flow patterns that we have. This is bubbly, when we have little bubbles of gases immersed in the liquid. When we have a wavy like motion movement, we call it wavy motion. When wavy pattern, flow pattern, we have plug when it's in this form, slug when we have it in this form. This is stratified, and this is annular when we have the gas and the fluid at the edges. Now if you are having a horizontal pipe, this is what we have. This is the kind of bubbly that we have there. This is slug, this is churn, this is whisper annular, and this is the normal annular. So these are the major types of flow patterns that we have, both for horizontal and vertical pipes. Now this flow pattern depends on the superficial velocity of the gas and the liquid. So let's say the gas is having more velocity, you can have one either of any of these. Unlike when the velocity of the gas is lesser, you can have the other one. So we're going to study how this superficial velocity of gases affect the classification of these flow pattern into these various things, and we're going to be into these various flow patterns, and we're going to be doing it using deep learning. So that is actually the essence of our study. So let's continue. Aims and objective of the study. What are our aims in this? We want to use deep learning to identify and predict flow pattern. That's number one. Number two is that we want to be able to explain the concept of deep learning so that we can know how to apply it in chemical engineering. And thirdly, we want to examine the effect of varying the architectural parameters on the efficiency of prediction using deep learning. So these are the aims and objectives that we'll be trying to achieve in this. Now let's look at the significance of this study. Why are we doing this study? What is the justification for this study? Now, artificial neural network, which is the method that we want to be using to do this, artificial neural network have been used to identify and predict flow patterns. Because of the increase in computing power, researchers have developed deep learning techniques which are of great significance in process design, as the determination of flow pattern is needed for pressure drop and other calculations in process design. Now, in many of these applications, algorithms based on deep learning have surpassed the previous state of the art performance. So this is why it's better we will study this, because we found out that when you're using an algorithm from deep learning, it's performing better than the former state of the art algorithms or models. So it's very, very important that we study this so that we know how to use deep learning to apply in the classification of flow patterns in two-phase flow. This research will add to knowledge and literature in finding out the best architectural parameters needed to run efficient deep learning prediction. Now, these are the various people that have studied on this and have gotten their results, and we are trying to work and improve on this. We have the work of Barnier in 1980 on flow pattern transition for gas liquid flow in horizontal and inclined plane. We have that of Barnier in also 1980 on flow pattern. This classification is done by electrical conductance. So they came up with all these, and from the last work we are able to get what we are studying. Now, what are the materials and methods utilized in this very study? In our research, we used in this research we are going to be using a feed-forward normal network known as multi-layer MLP, multi-layer perceptron. A feed-forward normal network consists of an input layer, one or more hidden layers, and an output layer. Each layer is comprised of small units known as neurons. Neurons in the input layer receive the input signals X and distribute them forward to the rest of the network. In subsequent layers, each neuron receives a signal which is a weighted sum of the outputs of the nodes in the previous layer and a constant term called a bias. Inside each neuron, a nonlinear activation function transforms this input and passes it to the next layer. The first step in using multi-layer perceptron is determining an appropriate architecture. This means that we must determine the number of hidden units, the number of hidden layers, the type of activation function, as well as the number of input and output variables. The second step involves determining a training algorithm to estimate the weights and biases of the multi-layer perceptron. This involves iteratively solving an optimization problem to estimate the network weights and bias so that the network output is as close to a desired output as possible. Now, applications. Where do we see two-phase flow in nature? You can see them in pneumatic conveying system. You can see them in cyclone separators. So whenever you hear two-phase flow, it means flow of both gas and liquid in a vessel simultaneously. You can see them in airlift pump, in geyser pump, in fuel injector, in water jet machining, and in slurry transport pipeline. Now, what results are we expecting or is expected of this research? In this research, it is expected that MLP, multi-layer perceptron, on a set is used to train some data So on a randomly selected sample, approximately 60% of the entire dataset was used for training. Approximately 20 was used for testing. So in the subsequent table, we're going to see the chosen multi-layer perceptron architecture and parameters used in the experiment. Other design considerations are the choice of ReLU as the activation function, the E1, E2 regularization penalties to avoid overfitting, and the number of epochs and enfolds, the number of cross-validation folds. Now this is the table 2 that is showing the perceptron architecture and parameters. We are using 11 input units considering the features. That means we are using 11 features in this. The hidden layer will have 3 hidden layers with 25 neuron each. That's what we mean by hidden layer topology. Then we'll have neurons at the output layer to be 6 because we are classifying into 6 various classes of whether it's wavy, annular, or any of them. The activation function we're using is ReLU. Loss function is mean square error. Number of epochs, training epochs is 1 million. Then the penalty weighting is 0. For 1 and for 2 is 0.0001, and the enfold class validation is 10. So in this paper, it is expected that we propose 3 types of data sets as input features and investigated the use of deep learning for the classification and prediction of 2-phase flow based on experimental data obtained from graph actually. Now we propose 6 types of input features and a corresponding architecture to precisely predict flow pattern. First, we show that the network can learn surprisingly well as using our chosen architecture and parameters allowed us to achieve high classification accuracy. Second, we show that the network can classify the different flow patterns with high efficiency. Finally, we achieved a high precision predicting different combination of classes. Now these are the references, the book we consulted as we are planning and doing this research work.